Hello everyone, this is Dr. Lennon, and today we'll be talking about exponential functions. So let's start out with the definition in standard form. So an exponential function, well, I'll tell you the form, but the main difference between it and linear functions is it's going to grow multiplicatively in the output rather than additively. So this is one that has the form and a lot of times with applications, the input is time, so we'll use t as the variable. So it looks like f of t, a function of t, looks like a times b to the t power. So again, as mentioned, this is characterized by a multiplicative change in the output for a fixed additive change in the input. That's one quick way you can recognize the difference between an exponential and a linear if you're looking at, say, a table of values. B is the exponential base. Which will be exactly what that multiplicative change is for a time step of unit 1. And the parameter in front, a, notice if you plug in 0 for t, you'll get a y value of exactly a, because b to the 0 power is 1. So 0a is the y-intercept. So I should also make two little clarifications up here. So there are two kind of restrictions. We're going to say that well, we'll say a is greater than 0 and b is greater than 0, and additionally b cannot equal 1. If b were equal to 1, then 1 to any power is just equal to 1, so that wouldn't do much. So those are some restrictions on the parameters above. So if you would graph these things, there's essentially two possible graphs. One indicating exponential growth and the other indicating exponential decay. So those two possible graphs, what do they look like? Well, let's draw them below. So one, exponential growth would look something like this. So it reaches a horizontal asymptote to the left, and to the right it explodes to infinity. So this is exponential growth, and it happens when b is greater than 1. So this is exponential growth, and that happens when b is greater than 1. And the other scenario is exponential decay, which is essentially just a mirror image about the y-axis. So this is going to look something like this. So this is exponential decay, and this happens when b is between 0 and 1. So some examples, if we want to do a couple quick examples, we could say just y equals 2 to the t, and over here we could say y equals 1/2 to the t. So those are examples of such exponential functions. So why don't we go to a graphing utility to go ahead and see what those look like. So as mentioned, the graphing utility I like, I put it on the syllabus, is Desmos, DESMOS.com. Really nice and easy to use. So we can just do y equals 2 to the t power, and we see our graph right there. And we also have y equals, we can graph this on the same plane. You can either do 1/2 or 0.5 and raise that to the t power, and we get the symmetric graph. And you can notice you can change b around and you'll get things that are steeper or flatter depending on what you're closer to. So let's just look at the 2 to the t graph. So let's say you had a base bigger than 1 but still smaller than 2, so what would happen then? So let's say we did 1.1 and we raise that to the t power. Then we get something much, much flatter. And if we did something bigger than 2, but still exponential growth, so 3, actually I don't need parentheses there, say 3 to the t, we get something that's much steeper. And you can zoom out and see that eventually these things if you zoom out far enough, they all explode eventually once they reach a certain critical mass. So if the base is smaller, it's going to be flatter in the growth case, and larger, it's going to be steeper. So anyway, let's continue with some examples. So similar to what we did with linear functions, we'd like to answer the question, how many points would you need to determine a unique exponential function? You might look at it, the curvature, and say, oh, okay, well, this is, looks much more complicated than a linear function. I'm probably going to need more points. Well, in the case that you know that the data is behaving exponentially and it's fitting exactly, in fact, since there's only 2 unknown parameters, you only need 2 points to determine what A and B are. Plug both in, you have 2 equations and 2 unknowns. Typically, you can solve that. So let's look at this example. So what we want to do here is we want to find the equation of the exponential function. That passes through uh, 2, 10 and 4, 75. So let's say, what is the equation? Let's remind ourselves, what is the form of the exponential function? It's y equals a times b to the t power. So we can plug both of those things in. I would ask you to take note of the 2 and the 4. With the method I'm going to show you, I would say you're less prone to make mistakes if you plug in the one with the larger input first. So 75 is going to replace y, and 4 is going to replace t. So I get 75 equals ab to the 4th, and over here I get 10 equals ab squared. And then the question is, how do I put these things together? Well, if they're both equal and I take ratios of them, I will also get an equation, right? If 75 is the numerator of one fraction and ab to the 4th is the numerator of the other, and 10 is the denominator of one fraction and ab squared is the denominator of the other, those fractions must also be equal. And the upshot to doing that is the a's will cancel. A divided by a will just be 1. And then with the b's, you can just subtract their exponents. So we end up with 7.5 equals b squared. And again, because b is required to be positive according to the definition, we only need to worry about the positive square root in this case. So the square root of 7.5 is equal to b. Let's say for this example we're just rounding to 2 decimal places. We could say 2.74 is approximately the value of b. In general, for homework problems, they're going to have different thresholds for how many decimal places you want to keep, or they may say exact, and if they say exact, you're going to have to just work with the square root of 7.5. So then we have, what do we know? We now know that y is equal to a times 2.74 to the t. So we can plug in either one of the 2 points for t and y and then solve for a. So for this part, I'm going to plug in 2 and 10 because the numbers are a bit smaller. So we get 10 equals a times 2.74 squared. And then we can just divide on both sides by 2.74 squared. And we get the value of a, which is approximately 1.33. Okay, so the question asks for the entire equation. So if you plug both things back into the standard form, we get y is 1.33 times 2.74 raised to the t, and that would be your answer to this question. So let's try one more example just to make sure that the process sticks. So same type of question, find the exponential function that passes through um, 2, 80 and 5, 40.96. So same deal, we're just plugging both of them in. So 40.96 would be AB to the 5th, and 80 would equal AB squared. So again, notice this, we can already tell that as you increase the input, the output is decreasing, which means this example is going to have to be an exponential decay example. So when we take the ratios, we end up with 40.96 over 80 equals AB to the 5th over AB squared. So this time we end up with 0.512 equals B to the 3rd power. So now remember, to undo B to the 3rd power, you're going to either have to take the cube root, or raise both sides to the 1/3 power. Some calculators don't have a cube root button, so you may just want to do as follows. 0.512 to the 1/3 will equal B to the 3rd to the 1/3. So then we end up with B having a value of 0.8. And then lastly, we want to go back and find A. So we know Y equals A times 0.8 to the T. We can plug in our numbers. I'm going to use 80 and 2. So 80 equals A times 0.8 squared. We divide by 0.8 squared and we get 125 is the value of A. So our answer here is Y equals 125 times 0.8 to the T. And there was no rounding here, all of those came out exact. All right, so because these outputs are changing multiplicatively, we can always think of them as changing. Multiplicative change corresponds to a percentage change. So a question might be, how does the exponential base relate to the percent change in the output? So the answer is, maybe an easy answer would be if you looked at, say, the previous example and pretended like the initial amount were 100 rather than 125. So if you had 100 and you plugged in 1 for t, you'd end up with 80. So there was a 20% decrease. So how did that happen? Well, basically, if we write the exponential base is equal to 1 plus r, r is said to be the percent change. So let's look at the previous, as we saw in the previous example. Let's make sure this lines up. What we can do is we can set 0.8 equal to 1 plus r and then solve for r. So 0.8, which was the base, would equal 1 plus r. And then if you subtract 1, we get negative 0.2 is equal to r. So that tells us that the quantity is decreasing by 20% each unit time step. The output is decreasing by 20% each unit increase in t. in the variable t. So one last thing, let's go ahead and look at, well, not one last thing, but one last thing in terms of the general form. We'll look at an application to compound interest after that. So we have another form for exponential functions known as the continuous form. So the continuous form of an exponential function is given by y equals a times e to the kt. So here the variables are y and t still, but the parameters are a and k rather than a and b. And e, if you have not seen it, is the constant known as Euler's number. That has value 2.71828, and it continues on and on. It's a number very much like pi because it's classified as a technically an irrational and a transcendental number. But for our purposes, basically that means the decimal expansion goes on forever and ever and doesn't ever repeat. This is often given for a variety of reasons. As we'll see, this function e to the t is going to be very important for taking derivatives and antiderivatives in calculus, amongst other things. It's so very important. But let's just make a comment for now. How can we translate between one form and another? So basically one can easily translate between continuous form and standard form by setting b equal to e to the k and solving for whichever ones you don't know. Okay, so let's just look at two examples each way, converting from standard to continuous and vice versa. So we'll say convert to continuous form. So A, let's say we have y equals 300 times 1.12 to the t. Again, if you see a function like this in standard form, you might want to ask yourself, what is the percent change? Is it growth? Is it decay? All those things. So this example is growth, and it's growing by 12% per unit time step. So let's change this over to the continuous form. So we have to figure out what k is. So we just set 1.12 equal to e to the k. So 1.12 is equal to e to the k. To solve for k, we need to take the natural log of both sides. So this is the only place we're using natural log right now. I will explain more next section what that amounts to, because we will be covering the inverse function of exponential functions, namely the log functions, next section. So k is about 0.1133, so our continuous form would look like 300. It would have the same initial amount times e to the 0.1133 to the t power. So that would be your continuous form for part A here. Notice again that 12% was the growth for the standard form. If you look at the k value, 0.1133, sometimes that's known as the continuous percent growth. and we'll maybe talk about how that relates in terms of interest in a moment. So let's do the same thing for y equals 78 times 0.9 to the t. Again, nothing really different. We just set 0.9 equal 0.9 equal to e to the k and take the natural log. So the natural log of 0.9 is equal to k. So negative 0.1054 is approximately the value of k. I just wanted to look at an example where we had both growth and decay. So the continuous form is 78 e to the negative 0.1054 times t. And that's all there is there. All right, continuing on, let's look at converting the other direction. So let's convert some continuous forms to standard form. So convert to standard form. So for A, let's look at y equals 700 e to the 1.3t. So here, e to the 1.3 is our value for B. So you can just punch that into a calculator and get an approximate value. So if we just leave it to 2 decimal places, we get about 3.67 as the value of B. So we have y equals 700 times 3.67 to the t. And if we look at B, we have y equals 1000 times e to the negative 0.2t. And again, we just plug into our calculator e to the negative 0.2. That's the value of B. So that comes out to about 0.819. I should use, when I use that squiggly equal sign, that just means it's an approximation, which means I'm rounding to some number of decimal places. So that's pretty universal notation in math. Just stands for approximately. So that's converting back and forth between standard and continuous. So you can always do that if you prefer working with one or another. Now, one big application is in the theory of interest. So we have two formulas when it comes to compound interest. So our compound interest formulas, and again, since this is an applications class, we're not going to spend time deriving these. In fact, the continuous form would come from finding a limit, which we will look at later in chapter 2. So the first one we'll look at is finite compounding. And the formula is A is equal to P times the quantity 1 plus R over N raised to the N times T. So we've got a lot of different letters here, so let's explain what each one is. So A is the future value, or you could think of it as the accrued amount. P is your initial investment, sometimes known as the principal. R is the interest rate, and this is as a decimal, not as a percentage. So if you had 15%, R would be 0.15. Or it could be a percentage growth rate. It wouldn't have to necessarily be interest. I would just say that's the most common. N is the number of times compounded annually. and t is the time in years. So if they ever give you a different time, like 18 months, let's say, then you would have to convert that to years. So t would be 1.5, not 18. So this is the time in years. And then on the flip side of that, we have continuous compounding, which means if you took a limit to how much money at a nominal interest rate you could make by just adding to the compounding, right? You could go, say, quarterly compounding, monthly compounding, compound every day even. If you could imagine compounding at every single moment throughout the year, that would be continuous compounding. And the formula is actually much simpler. So continuous compounding so that is given by the formula A equals P times e to the RT. So all the letters mean the same thing. And again, E is just the Euler's constant that we looked at, which is about 2.718 if you want to use a few decimal places. So let's just do an example where we use these formulas. Again, we're just kind of plugging and chugging here. Nothing too much to think about, but we just want to plug them all in to make sure that we can get the right answers. So example, let's go ahead and compute the future value. Of an investment of $30,000 at 8% for 5 years. Okay, so what do we know so far? We know that the principal is 30,000, so P is 30,000. The interest rate, 8%, would correspond to 0.08 as a decimal, and 5 is the value of T. So A, let's say we do it if we're just compounding annually. So that's a bit of a code for n equals 1. You could think about it that way. So we have A equals 30,000 times 1 plus 0.08 to the 5th power. So sometimes annually is given as just simple interest. It's kind of a special case of this compound interest formula. So the answer here would come out to $44,079.84. So that would be part A, if we frame that in there. B, let's suppose we're compounding quarterly. So a lot of times there's code words that indicate the value of n. So that's n equals 4. Quarterly is 4 times per year. So the formula alters a little bit, but not too much. So we still have the 30,000 in front. Then we have 1 plus the 0.08 divided by 4. And then in the exponent, we have 4 times 5. So depending on which calculator you use, you want to make sure that you're typing it in correctly. And if you need to put parentheses places, that you're putting them in the correct spot. But this should come out to $44,578.42. So that is... So I kind of frame these in just to indicate where the work is and where the question ends. Okay, so just 2 more parts of this example, and then that is it for the exponential function review. So let's say compounded monthly. So that is n equals 12. And again, it's going to look exactly like the above example, just everywhere we had a 4, now we are going to have a 12. So 30,000 times 1 plus 0.08 over 12, and then change the 4 on top to 12, 12 times 5, and what do you get if you punch this in? Well, we should get $44,695.37. notice that so far the compounding has gotten larger and larger, and our amounts have gotten larger and larger. We started with 44,079 for part A, 44,578 for B. Now we're up to 44,695. So in terms of a nominal rate, so the nominal rate is what they say. It's not the effective rate. The effective rate would correspond to what the analogous rate would be for a simple interest situation. Anyway, the nominal interest rate that we're working with here, they're all 8%. So the biggest amount you could earn here based on that nominal rate of 8% is going to be this case D. So this is going to be continuously. And the formula is actually the easiest. We just have to do A is equal to 30,000 times E to the 0.08 times 5. And that comes out to $44,754.74. So that's it for this section on exponential functions. If you have any questions, please let me know. Otherwise, this is Dr. Lennon signing off.